I'm going to go ahead and get started. Good morning, everyone. I'm going to talk today about how to utilize many of the tools that we learned yesterday with very little modification to run in parallel. Because a lot of us have large data, and a lot of us don't want to sit around and wait for our little laptops to finish analyzing our data. And we don't want to move it to our laptop, so we want to move towards analyzing our data where we first created it. So, first of all, all of this is fairly well documented on the YT website under Advanced Analysis Parallel Computation with YT. I'm going to also point out that if you'd like to download this talk and follow along so that you have reference, you can go to the YT workshop homepage. And I noticed this just before I got up here. It seems to be under the, instead of parallelism in YT, it's actually the, it's under advanced volume rendering. Okay, Matt's going to fix that in real time here. But once he does that, you guys will be able to download this. And there's a few pieces that you might want to look at your laptop while I'm showing something else. Okay, Matt says it's fixed, so go ahead and download that. Okay, so first of all, let's go through some of the capabilities. There's a whole list of here on the docs. There's different types of parallelism, which we're going to talk about. But in this talk, I'm hoping that you'll get an idea of which operations in YT are parallelizable. How do you run YT in parallel? I'm going to try to give you a sense of how many tasks you can reasonably use efficiently. That's kind of a tricky thing because data varies so much. And talk a little bit about best practices for running in parallel. So first of all, I want to go through the different types of parallelism. There's three main types that YT takes advantage of. The first is spatial decomposition. That means you have some algorithm for splitting up your data and handing off different pieces of your data to different processors to work on and collecting the results at the end. So these are things like halo finding, volume rendering, two-point functions, the radial column density calculation. All those things, you split up your data and you fork it off to different processors. The next one is grid decomposition. This is where you take your full set of grids in your simulation and you partition off each grid to do the same analysis over each grid, and then you take the final result and you incorporate it back in. So these are things that we've already seen, like projections, slices, cutting planes, 1D, 2D, and 3D profiles. All of these things loop over the grids in order to utilize as many threads as we can. Finally, there's object-based parallelism. This is anything that you may call embarrassingly parallel. Say you have 1,000 halos or 1,000 spheres that you want to do the same thing to each time. This is where you're going to parallelize over individual data objects. And so we provide a few helper functions that allow you to do this kind of cleanly and keep track of your results so you don't have to get into a bunch of MPI calls and take care of everything yourself. First of all, we utilize MPI for Pi, which is an open source package that allows a Python interface to the MPI calls. And one of the first things I'm going to try to have you guys do is install MPI for Pi so you can give this all a shot. So I tested this on Brian's laptop earlier this morning. If you don't have MPI for Pi installed already, I am fairly confident that if you have a Mac and you've installed pip, which it should be, you should be able to say pip install MPI for Pi, and it'll pick up your MPI run that is with the computer already set to go there. So I'd like everyone to give that a try. It may or may not work on a Linux machine, And if you have access to Nautilus, it should already be installed there.
I would also if you install via pip install.
Right.
Might get a bunch of warning, but just hang tight, and after a minute or two, it'll
Yeah.
be
Okay, Jeff says that it should work on Ubuntu as well. So could everyone give that a shot? It'll probably go out and try to grab a package, and it takes a minute or two to install. Yes, I believe that should be all that you need. Is anybody having difficulties with pip install MPI for Pi? What's so you may need to I should say that this only works if you already have an MPI installation on your computer. So you may need to install. It should, yeah. If you have developer tools installed from OS X, it should be on there. But and if it fails miserably, the backup plan is to log into Nautilus, and you should be fine. Is anybody still working on getting this going? Okay, trouble, or is it just going slow? Okay. Stephen, do you want to? Thanks. Anybody on this side still working on it? Having problems? Is it anything in particular, or? Okay.
You need MPI-default-bin, and MPI-default-dev.
Okay, so I'm gonna start going through the next pieces. If you haven't gotten it going, maybe look to your neighbor's laptop screen. So if it's not going at this point, just look next door to a friendly neighbor. Get comfortable. Okay. So in terms of launching parallel YT jobs, 99% of everything that you'll do in parallel with YT will require just throwing a -- parallel at the end of your script. So say you had some projection script called YT script.py. All that you would need to do is do MPI run -np, however many processors you're running with, your script name, or I'm sorry, you need a Python YT script.py, and then -- parallel. So before that, after the N, you still need to call Python. So what this does is it tells YT to initialize the parallel environment. It sets up MPI, sets up the global communicator, and then the internals of YT are ready to work in parallel. The other 1% of the parallel YT jobs are stuff that you're going to hand code yourself. Say you want to manually manage what MPI is doing and how it's splitting up your work. We are not going to cover this because that's just really a case-by-case example that doesn't come up that often. So we're going to go through our first simple example of running one of these scripts. What we're going to do is utilize the YT pastebin grab. So YT pastebin grab is a command that tells your computer to go out and grab a particular pastebin from the paste website on YT. So I've gone ahead and put up these paste bins last night. So if you do YT paste bin grab 2072 and pipe that or put that into parallel projection.py, it should go out and grab that script for you so you don't have to spend any time typing. So all we're doing right now is just this line here. And whoever finishes this first, let me know that it actually worked. Okay. So what that should look like is this screenshot here. To run that script in serial, you would just do like you've done yesterday. You'd call it with Python parallel projection.py, and it would just do its own thing. So go ahead and do that. You may need to change the location of the data path. This is where my data is in data // no mag2 hdf5 plot blah blah blah. So that will be the only thing you need to modify in this script. You can feel free to use any data set you want. This will work just fine on anything you want. This data set is a little bit larger than the Enzo Tiny cosmology, I think, so it'll take a little bit more time. Yeah. No, data doesn't have to be in a folder called data. That's just where mine is. Has anybody successfully run this script yet? Okay. Did it go ahead and print out the time that it's taken? Okay. Should be about a second or so. Okay. Oh, that's right. It takes about 10 seconds for this data set. Once you finish running that first script in serial, now all you have to do to run it in parallel is run this second line, MPI run -mp2. I'm assuming you may have 2 processors on your laptop. Feel free to use more if you like. And then at the end of this, you just add in -- parallel. It should run. It should make the same projection. It'll give you out the same results. And it'll hopefully show you a reduced time. I believe it only actually writes out once. Each of those processors will say saving file to this image name. Is that correct? Okay. So the reason why you'll see that twice is that it's so that this pc.save returns a list of file names that it's saved. And it needs to do that so that each processor knows that it's saved the same file names, so that it's consistent across all the processors.
So when I go back and run the serial again, it has to the second time.
Right. So the second time you run this, the processor itself will cache. It's like a hard drive optimization on your actual computer, and so it'll be faster the second time. But then it should still be even faster when you run it in two processors. Ah.
It shouldn't ever happen. It does happen on occasion. Have your path set right, and when you just type Python, you might pick up some other version of Python. So, like I said, that never happens. Path is like Python. We're type PYYT. So there's no dash. PYYT.
Right. So what John was mentioning is that if you have multiple Python installations and some of them may be linked with the right MPI or not, make sure that you use PyYT, PyYT, which will launch the correct Python in this case, if you're having that problem. So has anybody finished running both these scripts? Anybody having difficulty running either of them? What's happening?
Parallel, I get an overflow error if I'm not in two wires on, but only when I'm doing multiple. When I do it by itself, it's not.
Brittany, you want to take a look at that? Really? You added in the dash dash parallel? What? Oh, but it's because he didn't have dash dash parallel. I have slides about the quad tree stuff. Okay, anybody have any questions so far on what's going on here? Is everyone super excited about how easy it was to run this in parallel? Yeah. All right. We're going to go ahead and move on to some more motivation and talk about what's going on behind the scenes now. First, why do you care about what YT is doing in the background? Why should I spend some time talking about how YT partitions up this data? Well, first of all, it's your data. You know more about your data than the developers of YT can ever know about your data. You know how big it is. You know how many grids there are. You know how many threads it was originally run on your supercomputer. You know how to optimize your usage and your parallel usage of YT. If I've got this Enzo tiny cosmology, I know that it's a small data set and that I don't need to run analysis on 128 processors to get anything done. I know that I can just do it on my laptop. But if I have a huge simulation and I knew that it took 1,000 cores to run in the first place, I know in the back of my head that it shouldn't run very quickly on one core. So, what I'm going to try to show you and give you is an idea of how to run efficiently, how these things work in the background so that you have the knowledge to figure out what should run efficiently and what shouldn't. So first thing we're going to talk about is grid decomposition. This is where you loop over the grids, you apply some operation to that grid, and then you collect, reduce, and distribute the results to all the processors. This means that you might be joining image planes, you might be joining these adaptive projections that YT makes, you might be reducing average quantities and derived quantities. So in projections, this has a little bit of history to it. The original implementation utilized a image plane decomposition where your domain, if you're projecting down the x-axis, would be split into tiles, and each of those tiles would be given to a different processor to work on. This ends up having very bad load balancing problems for deep hierarchies where you may only have a few objects that you actually care about. However, it was somewhat slow, but it was efficiently parallelized when you had a naturally balanced data set where you may have refinement regions all over your box, and you have a fairly naturally load balanced data set. Recently, I guess in the last 6 months, maybe a year, Matt wrote this quad tree construction, which is a very, very fast implementation of doing these adaptive projections. Even for a serial processor, like a serial calculation, it's relatively quick for a 1024 cube data set with 7 levels of AMR. This is, on the order of maybe 100 seconds or so to do something of a fairly large operation. That said, it has a fairly inefficient parallelization because it has to go back and merge these quad trees, which we haven't figured out how to do a fast implementation of yet. So the old way, this is from the YT method paper of doing parallel projections. You can see that we had fairly good scaling down to up to a couple hundred processors, especially when we didn't have to do input and output. Sorry. My phone's just playing music or something. That's right. It's done. So anyways, this was taking for two processors about 1,000 seconds when we were running with the old style of projection. I ran this on the same data set serially on my computer at home, and the first time we ran a projection, it took about 1,000 seconds. Oh, sorry, this is with the new algorithm. The second time I ran it, it was about 300 seconds, and the third one, just projecting the ones data set, which doesn't have a lot of I/O or any I/O at all, it was about 200 seconds. And this is on a very large data set. This is 512 cubed and 6 levels of refinement, about 500 million cells. So this is pretty quick, even in serial. I don't mind setting up a couple projections because you only have to do them once, and you let it go. Per data set, sorry. Okay, so that was projections. Slices are even faster, and they rarely need to be run in parallel. But they also utilize a grid-based parallelization where you loop over each grid, and you fill up the adaptive slice image. Slicing that same big data set that I was just talking about takes only 6 seconds. I'm perfectly happy to wait that long to slice that large of a data set. One common analysis task that can utilize fairly good parallelization is the cutting plane, this off-axis slice where you may be slicing a galaxy disk and you have some angular momentum vector that you want to slice perpendicular to. This involves a lot of intersection checks with the various data, and you can get some good speed up from using multiple processors for this type of operation. So the next example I'm going to have you guys do is a parallel profile. This is a 2D phase object. And so I'd like you to do the same thing, YT paste grab 2073, and pipe that into parallelprofile.py. And once you've downloaded it, please again replace the data path with one of your own data or whatever path it is to any data set that you really care about. In this case, yeah, any data will be fine. Has that second paste bin grab worked successfully for anyone? Great. Is everybody seeing a little bit of junk at the first? Just delete the first line, I guess. Okay, well, whatever. Okay, so if you have some funky looking stuff that shows up, just get rid of that first line. So what this script is going to do, it's going to load up. Yes, sorry. Yep. Replace that projection with profile. What this is going to do is it's going to go out and get all of the data, create a plot collection, and then add a phase object that uses the entire data set to create a 2D phase plot of density, x velocity, and cell mass, and the third field will be the cell mass there. So I'd like you to run that in serial and then run it in parallel just to prove that this all works fine. Anybody successfully do this? Okay, getting a few. Anybody having this fail miserably? What does your script look like? Or which data set are you using? I don't know what's going on. Okay. Okay, who needs some more time on doing this? Everyone's now run their first parallel operation of doing a phase object. This should be very well parallelized because it's looping over each grid and there's lots of work to be distributed, especially between two processors. Because you're parallelizing over grids and that makes it a very parallelizable thing. Everybody okay with me going on to the next thing?
I don't know, my laptop is not stock with it too.
It may be an issue of like disk speed, you know. So if you're having two processors fight with the file system to get at the same data, it's not going to be as fast on something like a laptop as it would be on a parallel file system. So you may see something like that. So Nathan says he has a solid state drive in his laptop and it's about twice as fast to run in parallel. So it'll depend on hardware. This is where all this stuff gets more and more difficult and more and less tractable. Okay. We're gonna. I don't know if I have. I think I have an example about derived quantities. For derived quantities, what you have to do is. Oh, don't worry about it. There's two stages. First of all, it loops over each of the grids. It does the actual calculation, and then you have to do a reduction because you now have your two processors or n processors each with a total mass quantity. You need to sum those all up in some way and create the final answer. So there's a calculation stage and a reduction stage. Parallel jobs, again, this is a grid decomposition, so it distributes the grids to the different processors, calculates it, reduces it. This is going to be very efficient as long, at least parallel efficient, as long as the number of grids that you have in your simulation is much, much larger than the number of processors that you're using. So you're going to get a good load balancing between your processors. There's an example of how you do this. If you want to do another paste bin grab, 2074. This is going to go through and calculate the weighted average of velocity magnitude weighted by the cell mass. Again, feel free to use any data set that you like. How long is this talk? It's an hour. But how long is it? Okay. Yeah. So you may see that you get a faster than ideal speed up because some of your processors will cache the entire data set if you split it into two processors, and so they can just work really quickly. So it doesn't have to touch the disk nearly as much. So this operation also preloads the data if you're running an ENSO data set so that it's just ready to go. Anybody successfully run both of these? Anybody still need me to go over anything? Okay. We're going to talk a little bit about object-based parallelization. That's where you have many data objects and you want to do the same thing to them. This one is a much more involved script, but it's still fairly simple to go through. So you want to grab 2075. What this script is going to do is take your data set, create 10 spheres centered at random locations in your data set. Out of those spheres, it's going to go through and calculate a derived quantity, which I think is a weighted average. I think it's bulk velocity, actually. it's then going to split up that operation among your processors and return the results. So I'm going to actually exit my presentation here so I can go along in this. Nathan mentions that this will only work on the development branch of YT, so if you're using the stable, you might have difficulty. Yeah. Okay. That statement may or may not be true. So as you're going through this, once you've replaced the data set with your data set of your choice, this is going to set up the centers. It's then going to set some radius. This is my fault. Is anybody going to use a flash data set for this or anything other than an Enzo data set right now? Okay. If you did, you need to change this 1 to unitary because I screwed that up. You're going to get something very tiny probably if you leave that there. What this then does is sets up a storage dictionary called my storage, which is going to be a place where you're going to store all the answers from your various processors in the end. So you set up an empty dictionary here. Then instead of looping through your objects in serial, you're going to loop through, and for each storage container and sphere in this parallel objects iterator, this is basically something that splits up all of your spheres onto the number of processors that you have and is going to put everything in the my storage dictionary. You then go through and you calculate whatever you want. In this case, I guess it's the total mass. So you store that result in this sto.result is equal to the sphere quantities total quantity cell mass. And then we're going to give it a key to that dictionary, which is the way you identify your result. And in this case, I couldn't think of anything really to look at, so I'm making a string out of the sphere center positions, the XYZ positions here. So at that point, it'll go through and run the analysis, splitting up the objects onto the various processors. And in the end here, we're going to use a way to get at the rank of the processor that's running. And on the root processor, we're going to print out the keys and the values of the result that we did. Has anybody run this successfully? Great. It should have printed out, and you've run it in one processor and 2 processors. Great. Numprox here is actually at the top, around line 19. If you set it to 0, it's going to go out and find whatever the MPI COM world size is, the total ranks that you're running. You could also change that to any number that you're... I think you need to set it to something less than the MPI run that you give it, but that just gets set somewhere else. And you don't even really have to specify it here. If you didn't have numprox in this parallel objects, it would just set it to be the number of ranks that you have. So whatever you called MPI run with. Anybody have any questions about this parallel object iterator? So all of the operation that we're doing here is loading the data on demand. And so when you split these up, each processor doesn't have to load in all the data. Each processor only, it temporarily has to load some of the data because then it has to cut it down to each one of these spheres. But it shouldn't be a large overhead in terms of loading up an entire data set on each processor to then run this. But it'll depend on what you're doing. For grid-based and object-based parallelism, there's very little I/O overhead because you're splitting up all the I/O and all the objects that you're working on. For the volume decomposition stuff, the spatial decomposition, there's trickier pieces to consider. Nathan?
A general comment about parallel objects. So, at least for my data set, parallel objects is the greatest thing since sliced bread because I have thousands of plot files. My almost real time because I can run it on hundreds of processors and clusters. So I can look over all of the plot files very, very quickly. So your time is much more valuable than CPU time on the cluster. So remember that. Parallel objects.
Yeah.
I can develop it on my notes. The parallel option how that looks again? Like this last one.
Sure. So what this does is so in this case, what we've done is create a set of objects. Oh, whoops. All of these 10 spheres, these 10 random spheres. I made these so that we had something to iterate over. And what this parallel objects does is take that list of objects that you want to do something to and partition them out between the two or n processors that you're working on. And so each processor works on some subset of those objects, and then you can store those results in this my storage dictionary, which you can then use later in your script or just write out, and that's what you wanted out. So how do you reduce the data? Yeah, so it'll depend on what you're iterating over. So in this case, you're iterating over these spheres. And so when you do this operation right here, this is where all the data I/O occurs. And so each one of those only does the data I/O for each processor, for what it actually is working on. If you were doing something else, depending on what the data object is, it might require reading in all of the data or do something like that. So it'll depend really on what you're doing. Okay, I'm going to go ahead.
So what it's doing is it's pushing a new MPI communicator on top. So all of the previous operations that would normally have been done globally are now being done just on that new MPI communicator. So depending on the specific operation that you're doing, like Sam said, you might touch exactly as many files as you would have had you not been doing parallel objects.
As long as
but now
you
you're
can
doing
define
it across
a list
5 work
of
groups or
objects,
something like that.
you can iterate over them. So if you had I have this list of parameter files, a list of PFs. I could put that in, and I'm going to say, I'm going to do a parallel object iterator over the PFs. And then in each one, you'd have access to those individual PFs. So time series analysis, this is something that works really well for that. And Britton's going to have an example in the time series talk later today, I think. Okay, I'm going to go over a little bit of spatial decomposition, but this is a fairly complex topic, and you don't. It varies so much from data set to data set that your mileage may vary here. John? So, yeah. 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 Okay, so spatial decomposition, these are things like halo finding, 2-point functions, and volume rendering. Halo finding, there's 3 different versions of halo finding. There's only one that's parallel, which is parallel hop. One issue is that, right, is that right? Or is
can run in parallel, but this can't go as big.
Okay, the other ones can run in parallel, but you can't do as large of a data set. There's increasing memory overhead because you have to hold more and more extra data as you move up this ladder here. But how these operations work, at least for parallel hop, is it partitions up the volume into rectangular solids and then distributes those pieces of the volume to each processor runs analysis, grabs some extra slabs and does some more analysis, and finally concatenates all the results into one halo finding list of objects. But the main idea to get in your head here is that it's going to partition up the volume spatially, do work on those volumes, and then bring it all back together. Now, if your data is naturally unbalanced, this may not be efficient. And so it's just something that you have to keep in mind, that your parallelization will only work as well as your data, in this sense, is parallelizable. I'm not going to talk any more on the parallelization of halo finding. I think halo finding itself will be covered at a later part of this talk, of this workshop. 2-point functions are where you're doing some calculation based on a spatial coherency. And this again is parallelized by domain decomposition into bricks. It uses MPI to communicate between processors to talk to each other. And there's a whole section on this on the website here about what the best practice is for doing these efficiently in parallel. And there's also examples online. The final thing I'm going to talk about is volume rendering, which we'll be getting into later today. Recently, there was a push to provide 2 layers of parallelism in the volume renderer. It used to be that the only way was doing a volume decomposition using something we call an AMR-KD tree. This attempts to split up the domain into as equal chunks as possible, depending on your number of processors. Recently, we've developed a way to do image plane decomposition, such that now each image plane itself can have some number of processors working on that piece of the image, and within that, they split up the domain into an AMR-KD tree. And so now you have 2 levels of parallelism that you can get out of this module. That means it gets slightly more complicated, but it allows you to do larger and larger renders of larger and larger data. As I said, this AMR-KD tree splits the domain up into the number of processors that you're using. Right now it's best when the data itself is naturally well balanced. By that I mean is that if it's an AMR data set, there's AMR everywhere. At the end of this process, when it's done with each processor working on each piece of the image, there's a binary tree image reduce so that you go from n images all up into one single image. We'll have more examples of the rendering module later. And I basically said this, so I'm not gonna cover this. One thing that you'll find is that for the 2-layer parallelism, you have to have one extra call to save out your image so that it concatenates the multiple images into one final image. Just going to give you a few notes and warnings to end here. As I said, there are these 2 versions of the parallel projection algorithm. If your data is more well suited to the old method, you can always go in and replace it by, at the top of your script, saying pf.h.proj, which is the projection algorithm, the projection method. You can just set that equal to the old one, which is this pf.h.overlap_proj. And then if your data is a big AMR everywhere that you need to run lots of tasks on and need to save a little bit of memory, then you can just do that. Finally, a final note is that the volume rendering right now, the KD tree can only use a power of 2 processors to decompose the volume. I'm working on fixing this, but if you run with MP of 100, it'll just act like it has 64 processors. It'll still run, it just won't be as efficient as you thought it was going to be. Now there's additional tips online, and with that, I'll end.